Okay, hello and welcome to our Wednesday press briefing at the European Planetary Science Congress in Nantes. We're delighted to have updates on two missions. One that has been producing some fantastic results, which we will hear some more about in just a moment. That's the Dawn mission to Ceres. And then we will hear about a future mission, the AIDA mission, which is looking to deflect a binary asteroid system. So we're going to start off with Dawn. The mission principal investigator, Chris Russell, will give an overview, and Raymond will give some further updates on results. We're going to have a time for a couple of questions in between the two presentations, just while we change over the presentation display. If you're watching this on the live stream, please do send us some questions either by email or tweet us using the hashtag EPSC 2015. We will be checking for anything marked with that. So, right, I will hand over to Chris.
Okay. Thank you, Anita. Okay, the reason for our being here today is that we want to give a little explanation of where we are in the mission, because the mission moves along, but we don't get all of the science at once as you do on Pluto. We go through and evolve in what we're doing. So we're going to give you an idea of where we are in the mission to date, where we are in our analysis, and also a little bit of insight into tomorrow's program for those of you who are in Nantes and will be able to go to tomorrow's session. I'll give you a few words on what we're going to be able to say. Now, the first thing that I think is important is how Dawn obtains its data. It's in a polar orbit and circular, and it just basically stares down at the surface and maps the surface. Now, we had very high altitude to start with, which we called rotational characterization. We have now moved down, completed the survey orbit, which was at 4,500 kilometers altitude, and that's where we took the complete VIR coverage of the surface for getting the mineral composition. We also took clear and color imagery with the camera. We finished that in July, and we moved then down into the high altitude mapping orbit where we are now. That gives us stereo imagery and higher resolution VIR data, and we get a better idea of what the composition of the surface is and the topography. And then finally, after we finish this phase next month, then we will move down over a period of about 2 months to lower altitude called the low altitude mapping orbit, where we can get our gamma ray and neutron measurements and improved gravity data. But we will also operate the VIR spectrometer and also the framing camera, but they will not be necessarily the prime instruments, although if we go into a extended mission phase, they will be playing a very important role again there. But we're not going to leave Ceres. We're going to stay in Ceres orbit forever, and we will not be able to operate eventually because we'll run out of attitude control gas. But we're hoping that we will get not only to the summer of 2016, but several months past that. Oops, sorry. Thank you. Okay, the first image that I have to show you is a mosaic of the digital terrain model, and the reds are high. There's this map over here is a duplicate of what's on the screen there. It also has the names that have been approved by the IAU. We're in the process of doing that. We justify what features will need names because of scientific study, and then we send that list into them, and they approve the names that we've selected from a list that has been pre-approved for that particular purpose. This height-colored survey mosaic has a resolution of about 400 meters per pixel, and it has 32 names of craters and 1 Montes on it, but not the Lonely Mountain. That name is still under consideration by the IAU, and we should learn about it soon. We can see that there are lowlands and highlands on this body, and the Aquitar crater is in the highlands over here. That's where the bright spots are. And then another interesting area down to is a lowlands area, and we're studying both of those and contrasting them to try and understand the body better. Another way we understand these bodies is to compare them against other objects in the solar system which we'd explored earlier or we're exploring contemporaneously. And so Pluto, it was really good that the New Horizons made those measurements this year so we can compare ours against theirs, and there are some similarities and there's some great differences because of the place in which these two bodies were formed. We also compare against the icy moons. Here we've shown Dione and Enceladus, icy moons of Saturn, and there are again some similarities to processes on those icy bodies, and then some important differences. Here are some craters. A crater that we saw on Vesta is on the left-hand side of the screen. And it is got bowl-shaped and it's more round. The one on the far right side is from Rhea, and it's an icy moon of Saturn. The crater's more irregular. It's got an irregular bottom, steep walls. And in the middle is a Ceres crater of a similar size. And it also is irregular in shape and has steep walls. But in this particular case, there's a smooth floor. And, you know, how did that happen? Was that melt of some sort? And what is the material that melted, if it is melt? And we're looking into questions like that of why are the craters different on Ceres than they are on Vesta and Rhea. We have some difficulty looking inside Ceres. We can use gravity and the overall properties. We can use modeling. And our ideas of Ceres that were formed from the geochemical analyses of the body and the simulations of the evolution of Ceres give us a picture of probably having a small condensation or at least dry silicate core, and then maybe a hydrated silicate material going out almost to the surface, perhaps some ice layer, and then a clay, dusty material, very dry material on the outside. But our cameras don't poke into the interior. We have to infer that from its properties and the gravitational field that we measure. But the outside of Ceres is very interesting. This is a color mosaic made from just ratios from, or basically stretching the color, stretching blue into, there's subtle variations in the blue. We make them look a little stronger here, and then stretch in the other direction into the reds. And you can see that there are regions of quite different color. And I'll get up here, I don't know if you can see very well, but, and I can't see because of the reflection, but there's an interesting blue ring here. We have absolutely no idea what that blue ring is due to. This is the Aquitar crater. It's unusually close to this strange feature here. And there are streaks across the surface, subtle, but they point back to the Aquitar crater with its bright spots. So we're poking at this and we're looking for ideas, but we haven't solved the problem yet. So here's a topographic picture of the Aquitar crater with its bright spots. Again, I apologize, we haven't solved the source of this, the white material. We think that it's salt that somehow has made its way to the surface. We're measuring the contours, trying to understand what the surface variations in that crater are telling us. This is a topo on the right, a topographic map of the area around the mountain. Again, we're having difficulty understanding what made that mountain. We've been getting many suggestions from the public, and one really caught my imagination, was sent in by Lauren Markle, a member of the public who's been following the Ceres exploration. And he looked at our mountain and he said, well, you know, many years ago I was walking through the forest and he found some ice structures on the ground, and the air was cold and the ground was warm, and these ice structures started just poking out. Each one of them had a rock or something like that protecting the surface, making it cool, in fact, keeping it cool. So he proposed that maybe the ice mountain was our Lonely Mountain was some sort of ice construct. So we're taking suggestions like this very seriously, and we will be trying to understand the stresses in ice. I noticed that that Pluto also has mountains that look an awful lot like the one that we found on Ceres. But I'll end with one big surprise. What is on this particular figure on the left is the counts from our gamma ray and neutron detector. And here these are due to energetic electrons, and they came from the sun. We've seen these before, and it goes up and comes down over a 3-day period. But something that we'd never seen before, not at Vesta and not at Ceres, until this particular day, were these little these little bursts of noise on the trace, and then we said, well, you know, these repeated 3 times. You know, what's the period of repetition? Well, what's the orbital period of our spacecraft around Ceres? And so we plotted them up in a solar-oriented coordinate system. So we had the solar longitude along here, and the latitude here, and all of those bursts occurred on the same part of the orbit, exactly one orbit after the other. Then they went away, and so something, you know, we did not expect that Ceres had any influence on the solar wind environment or the plasma environment. We were totally surprised by that, and we're looking into that. Okay, so tomorrow I will start off and, like today, just set the stage. Ryan Park is going to tell us about gravity and probing the inside. Prisker is going to give us a shape model that we can reveal features that we don't see with the cameras easily. Carol is going to tell us what we can learn by combining shape and gravity. Tosi will tell us about temperature and thermal inertia from the VIR investigation. Junyoung Lee will tell us about dust as a possible indicator of a weak atmosphere. Then there's 4 authors talking about cratering on this unusual surface, and a couple telling us about the VIR constraints on the spectral composition. Then Lee and Ciaranello will tell us about the photometry of the surface. This is important for detecting change. We are very interested in whether the surface of Ceres changes over time or is constant on the length of our observations. And it also, photometry helps us make good images. We have a VESTA talk on how VESTA has evolved. We have a talk on the mineral composition, geology, and color. And then in the late afternoon, we have 13 posters, including the first geologic maps. Harold, did you want to say anything at this point, or just wait for questions?
I think we could just take questions.
We have time for a couple of questions.
Leo Enright from Irish Television. These energetic electrons, is this a temporal effect? I mean, is it happening at the same time or at the same position on the surface?
They occurred on 3 successive orbits in the detector that was pointing towards Ceres. So the electron detector was pointing down towards the surface, and the electrons were coming back. I presume they're bouncing back from Ceres, but what it is that bounces the particles back into our detectors and possibly accelerates them is unknown to us at the present time.
But is it the same location on Ceres on each orbit, or is it?
Oh no! If you do put it into the geographic system, it's a different position each time. It's something to do with the way Ceres interacted with the solar wind at that particular time.
Okay. Could I ask another question on a rather different subject?
Sure.
The detection of water by the Herschel team last year, you made some reference to it at the plenary session on Monday, which caused some surprise, I have to say, among European scientists who wondered what the authority was for suggesting that the results might not be as certain as they believe they are. Could you discuss that?
Yeah. I may have phrased things not as well as I should have on Monday, but basically that there is some dissent in the team about the ability of those measurements to point to a point, any place on Ceres. They agree that the water was detected, but not necessarily a spatial reference for that water observation. So we're basically buying some of the story, but not all of the story. Okay.
There was a suggestion that because you couldn't see it, it was easier just to say that there was something wrong with their results.
No, it was a question of how the error, the standard deviation of the measurements should have been calculated. It's as simple of, what is the baseline that you calculate your standard deviation from, and it's that simple.
And if I might just one final follow-up on that, because I do think it's important. This was a result which got a lot of attention 12 months ago. Is there some way of resolving this? Do you think that at some stage you will have a capability to produce data which either nullifies what they're saying or negates what they're saying or proves it? And also, is it possible that the effect that they were seeing was something to do with the position of Ceres in its orbit? And if that was the case, will you be around long enough to see Ceres at the same time again?
We do not expect to be taking data for a long period of time. We'll go into the low altitude orbit and last as long as we can, but it may be the order of 6 months at most a year, and that won't take us very far around. Detecting water ourselves, we do not have the spectrometer that Herschel has or had, so we will not be able to duplicate that, but we would hope that we would learn enough from looking at the surface to understand it better, to understand what geolocations there are for possible water sources. But we don't, at this stage, we don't understand the surface well enough to do that.
I don't have anything to add to that.
Okay, thanks. We will be taking more questions at the end, both for Chris and Carol and for Patrick and Michael. But now, just to keep things moving on, we are going to move on to the Asteroid Impact and Deflection Assessment Mission. This is a joint mission between ESA and NASA. First of all, we're going to hear from Patrick Michel, who is the lead investigator for the AIM European part of that mission, and then we will hear from Michael Küppers, who will give the European Space Agency point of view. So over to you, Patrick.
Okay, so good afternoon, everybody. So we're going to take you from the largest asteroid that we know, Ceres, to a very small one with this mission AIDA. So AIDA is effectively a joint collaboration between ESA and NASA, and the plan is to fly 2 separate spacecraft. One would be an impactor and another one would be an observer, in order to make a first test of what we call the kinetic impactor techniques in order to deflect an asteroid. So in fact, Michel will tell you about the techniques and the spacecraft and the mission itself. I will more insist on the relevance of AIDA for planetary defense and also science, because in fact AIDA is relevant for many disciplines. The knowledge that you get from this kind of mission, which aims at characterizing a small asteroid, its internal structure, its shape, its gravity, and other things, is actually relevant for planetary defense, of course, because if you want to deflect a body, better know what the enemy is made of. Science, because these bodies are the bricks, the remnant of the planetary formation era, and then can tell us a lot about our solar system history. Human exploration, because as Michel will show you, we want to deal with this body by deploying some landers, interacting with it mechanically, and all this knowledge about how the material behaves in a very low gravity environment is very important in order to design proper tools for a human, for instance, in order to make sure that it stays on the surface. And then, of course, resource utilization, because as you know, there are some projects to mine asteroids, and the same problem arises. How do you interact with the surface in a very low gravity environment? What is the best way to do it? So AIDA by itself, in full, is a kinetic impactor test. And just to give you the basic concept of kinetic impactor method, so basically you have a small projectile which carries a small mass. It impacts into the target. The target can be very big, so if you just give the mass of the projectile to the target, the deflection may not be very high. However, if there are ejectors that are produced and that are going in the opposite direction, then of course the momentum that they carry is added to the target by conservation. This is a famous law in physics. And therefore, the more ejecta you have, the bigger deflection you can do. So, of course, all this depends on the internal structure of the body. Impact physics tells you that the outcome of an impact is very dependent on the internal structure and surface properties of the body. So, the objective of the AIM mission, which is the Asteroid Impact Mission component made by European Space Agency, is actually would be the first mission to measure the properties that really help to interpret the impact of a kinetic impactor and therefore inform mitigation. So the measurements we want to do are to measure the mass and the shape of the target, which are effectively the first parameters that contribute, the dynamical state of the target, we'll see why, and of course the surface, subsurface, and internal properties, because these are the regions that the shock wave will see from the impact. And therefore we need, if we want to interpret correctly the impact, to have these initial conditions basically. This is also very important for numerical models, because if we want to validate the numerical simulations, which are, numerical simulation can tell what they want, so you need a validation point, and this would be the first validation point at large scale, at asteroid scale, and very well documented, because you would have the initial conditions, including the target properties, and the outcome when we observe the outcome of the impact. And just to show you two movies qualitatively which shows you how the outcome of an impact depends on the internal structure. On the left side, you have so the two snapshots you see here are initial conditions, where we start with a body of 10 kilometers, the yellow one, and a projectile arrives at high velocity. And the difference between the two is one is non-porous, think about the monolithic basalt, and on the right side you will see a sort of pumice-like material. And just qualitatively, you see on the basalt case that you would basically destroy the target, and on the porous case, then you see that actually the outcome is very different qualitatively. On the right side in particular, you see that basically you compact. You don't really have cracks shown. It's more like compaction, because when you have porosity, the shock wave is dissipated by the crushing of the porous regions. And what we learn from that is that in principle it's harder to deflect a non-porous body, because you have more dissipation than a non-porous one. But of course these are just simulations, and we need to validate that, because otherwise, if you rely on numerical simulation to make your first deflection attempt for a real case, then it can be very scary. So this is a target that is actually the objective of this AIDA mission. So it's actually a binary asteroid. 15% of the nearest object population is made of binary objects. Binary means double objects. You have a primary, so a big object at the center, here about 750 meters, and then you have a small natural satellite, which is here 160 meters. And the target of this mission is actually the small satellite. Of course, it's much more challenging to deflect the secondary than the primary, because of course the satellite is very small compared to the first one. But what we want to do is to measure the perturbation due to the impact on the orbit of the satellite around the primary, because it's actually easier to measure this kind of deflection than the deflection on the orbit around the sun. So this is very interesting, because there are many science implications for that. Thanks to the observer spacecraft, which will characterize the object, we can also better understand how the binary system form. And as I said, they correspond to 15% of the NEO population, so it's not a negligible fraction. And in particular, if you see the shape of the central body, it is what we call a top shape. So basically it's an oblate spheroid. And as you can see, all these images which show radar images of a few of these multiple systems, there is a tendency to have about the same shape for the central body. And you see in particular there is some sort of equatorial ridge that you can see on these. And maybe that tells us something about the formation mechanism of this binary, because this seems to be very systematic. And in fact, to form binary, you have several scenarios. One is what we call tidal disruption. It's the same thing that happened with the comet Shoemaker-Levy 9 in 1994. This comet made the first passage around Jupiter, and because it was very fragile, the forces due to Jupiter broke the target into 21 pieces, and then they impacted Jupiter later. So, in fact, this kind of forces acting during a close passage, if the body is fragile enough, could disrupt it. And in some cases, the disruption can be the outcome can be a binary formation. And this is shown here on the movie, where you see this kind of fragile body. And here we pass close to the Earth, and you see effectively that you form a binary. However, as you can see, the central body is not at all a spheroid shape. It's actually very elongated because of the way the body is torn apart. So this kind of mechanism is probably not the one which is dominant in the formation of binaries. So we need another one which can explain the shape and is also systematic. So it turns out that in the solar system you have gravitational forces, but you have also thermal forces. And there is a thermal effect called the Yorp effect. I won't explain what it is because it's complicated, but basically the outcome of this effect is to either spin up or spin down the body. And it has been actually measured on the asteroid called Yorp here, which is speeding up. So what we are looking at is what do we do if effectively we take a small body and we spin it up? What can happen? And in particular, because we think that these small bodies are rather aggregates than monolith, for some reason that I can explain later, then we started with an aggregate, and we started to make a spin-up simulation. And as you can see, when the body has a rotation increasing, the particles that are at the pole, they fall at the equator where the centrifugal force is maximal. And when this force exceeds the gravitational force, then of course the particles escape, and they can in some cases reaccumulate and form a secondary. And the way this mechanism works makes the shape, which is this kind of a top shape, oblate spheroid with an equatorial ridge, as you can see here. It's simply the way the particles fall on the equator and escape. Of course, this is a radar image of a 1999 KW4, which is a real asteroid, and you can see that it's really resembling the shape I just showed by the simulation. But it doesn't work on all cases. For instance, when the core is too small, so if you put a solid core inside the body, then it doesn't work necessarily. It tends to elongate, and you don't form a satellite. So that tells us that the binary formation is highly dependent on the internal structure you have. And even more, in fact, there are other mechanisms to make binaries. So there is this mass shedding that I just explained. You could also have a fission of the two bodies, and one of them could form the secondary, and in some cases explain also the primary shape. But these two models are very different prediction on the internal structures. And therefore, by measuring the internal structure with AIM, then you can really discriminate between these two models. Moreover, since this has implication on internal structure, it's also very interesting if we want to understand the history of the solar system, because these bodies are the outcome of collisions. So the structure they have now is the consequence of all the collisions they suffered since they were born. And the role of collisions is very, very key in the solar system history. Planetesimal formation started with collisions of dust between them. Then you grew to planetary embryos. And we always have this problem of what is the impact energy that leads to accretion rather than disruption. And usually we use ad hoc parameters because we lack a good understanding of the physics at play at this kind of scales, which is starting at 100 meters to kilometers. Then you go to the era of planet formation, where you end your planet still by accretion. Then you have giant impacts, and now we are in the era of collisional disruptions, as we see in the main belt, and as is witnessed by the craters on Ceres, for instance. So by understanding the physics at play at the real scale of asteroids, then you can really feed with more reliable ways these models of collisional evolutions of the solar system. So this is what is on these slides. Collisions and internal structure are very important to understand because they serve as a tracer of the original evolution of the solar system. Because we all think, we think that the bodies which are now rubble pipes are formed by this kind of disruption and reaccumulation, but don't really know what is the real outcome of these kind of things. So I think I'm almost done. I just finished by one fundamental question that this mission will also address, is how an external solicitation is actually influencing the surface of the body. In particular, if you land a lander on the surface, how it will bounce, how the surface will react. Same for the impact. And this is very important because this is in a very low gravity environment. And of course, the material, especially if it's sand, will react differently depending on the gravity level. And we still lack a clear understanding on how the surface behaves in a low gravity environment. And as I said before, this has consequences for the preparation and the design of future missions. So I have a general conclusion, but probably I will give the speech to Michel, because he will probably give back the conclusion again.
Okay, after Patrick's introduction to the science of the mission, I'm now giving a short overview about the asteroid impact mission itself. This is a graphical visualization of the general mission setup with the DART mission run by the Applied Physics Laboratory in the USA and NASA will impact the secondary of the double asteroid. And this impactor is designed to a size, it's about 300 kilograms, impacting with 6 or 7 kilometers per second, that it changes the orbit of the secondary around the primary, so it changes the orbital period, but it will not remove it out of its orbit, and it will also not destroy the secondary. And AIM, the ESA contribution, will be there before, during, and after the impact, to characterize the asteroid before and after, and to see what has changed with the impact, and provide some information about the effect of the impact beyond the change of the period that can even be observed from the ground. This will take advantage of a close approach of the target called Didymos to Earth in October 2022. So this 0.1 AU, this is roughly 15 million kilometers, which is of course not a danger to Earth, but it's a close distance on solar system scales. And to reach this in October 22, there's also a fixed launch date in the second half of 2020. So there are overall 3 goals in the mission. The main one already mentioned, asteroid impact mitigation, to be prepared for the case that some other asteroid could be a hazard for Earth by a potential impact, and to test one of the possible deflection mechanisms. It's also important technology demonstration, so we will use this mission to try for the first time optical communication between an interplanetary spacecraft and Earth. So in addition to the usual radio communication systems, there will be a laser system to try optical communication with the help of ESA's optical ground station, which is a 1-meter telescope in Tenerife. And the third important goal of the mission is the science of a binary asteroid. This is what Patrick already told about. So yeah, many firsts. It's the first time that we try interplanetary optical communication. We are also trying to take some CubeSats and have a small lander on the secondary of the asteroids and inter-satellite links between all those satellites. It's the first time to measure and characterize the asteroid deflection, where the deflection itself will be provided by the NASA part of the mission. And it's the first mission ever to a binary asteroid. That's a small sketch of the target. So the larger one is a bit less than 800 meters. The second one, that one that will be impacted, around 150 meters. Actually, Patrick had those numbers with more significant digits, so the system is known quite well. And the distance between the two is only a bit more than a kilometer, so the graphics is roughly to scale, with the exception of the spacecraft, of course, but the 2 asteroids are roughly to scale there. So the mission scenario, the broad mission scenario is launch end of October 2020, more or less, 2 years of interplanetary cruise, arrival mid-2022, and then the operations at the asteroid use largely the experience from Rosetta. So there will be a first characterization phase at a distance of around 35 kilometers or so, to get the shape, the gravity field and so of the asteroid, to know it well enough to go close. The actual detailed characterization will then be done from a distance of approximately 10 kilometers. Then AIM needs to get very close to be able to land a small lander on the secondary, needs to get very close to the secondary from that, and a while after that's back off, to be not too close when the DART spacecraft is actually impacting, and to be protected from the dust that is expected to be ejected. And finally, there will be a second characterization phase to see what has changed due to the impact. This whole mission at the asteroid is expected to take from about May-June 2022, a bit more than half a year to end of the year 2022. So the payload, there is of course a camera which is for both for navigating at the asteroid, but also for science to understand the surface of both asteroids. A thermal infrared imager that will measure surface temperature and deduce from that the physical properties of the thermal of the surface layer, especially of the rate of change of the temperature at sunrise or sunset. That gives an information about the heat conducting properties on the surface, and therefore which type of some information about which type of material there is. There is a small asteroid lander which is essentially a box that is dropped on the surface of the asteroid. There's a similar lander on the Japanese Hayabusa 2 mission that's currently going to another asteroid, and essentially something close to a copy of that will be carried on AIM. There is currently there is space for a few CubeSats. So CubeSats in the simple form, it's a 10 times 10 times 10 centimeter box, and there's space for up to 6 units of this, and they can be combined up to, one version is to have 2 CubeSats of 30 times 10 times 10 centimeters, and possible payloads for that are currently being investigated. Then there's the optical terminal to the optical telecommunications from Earth, and it's currently being investigated to use this as well, this laser as well as a laser altimeter to measure the distance between the spacecraft and the asteroid, and to get further information about the surface of the asteroid, because the topography can be measured accurately with this, and it would also be helpful for navigation. And finally, there are 2 radars, a high-frequency radar that will measure the subsurface structure down to a depth of a few meters or 10 meters roughly, and a low-frequency radar that sends waves between the mascot lander and the AIM spacecraft to get the global interior structure of the moon of the asteroid where the mascot lander is supposed to touch down. So in conclusion, AIM is a small mission of opportunity. It's the first investigation of the kinetic impactor technique in combination with DART. It will provide asteroid science, and various technologies are intended to be demonstrated for the first time. Thank you.
Okay, are there any questions from the audience?
Hello, Lizzie Gibney from Nature. What are the advantages of optical telecommunications in space? Why do we want to be able to do that?
So in the case of AIM, it's a poor demonstration, but in the next step, using a larger telescope, one can get a higher data rate than with radio communications. Honestly, in AIM, this is with a 1 meter telescope. It's not yet the case, but it could be for future missions.
Bonjour, Samir Vendouche, School of Future, the international network about understand science and astrophysics with younger people around the world. And I would like to know what is your project, and what do you expect about the CubeSat, and use a small technology compact satellite to take more easy to find money, and to have a more regular mission about that.
So indeed, the CubeSats are would be a financially small contribution. Of course, they still need the main spacecraft to get there. And there are several concepts under study what could be done there. So some are trying to stay in the asteroid system without landing and getting additional investigations that are not on the main spacecraft. Also getting additional information by getting closer to the asteroids than the observing spacecraft. Others will try to land either on the primary or on the secondary and have additional simple instrumentation to investigate it. There's also one concept which essentially tries to have in one of the scope stops a large number of small chip card sensors and get a large number of data points. So there are many concepts being investigated about what could be do with this CubeSats, and I think the selection will be done by end of next year.
Leo Enright from Irish TV again. Just actually following up directly on that question, has there any thought been given to opening up the CubeSat opportunities to, for instance, colleges? Or is this something that you think will have to be farmed out to industry? In other words, can it be part of an outreach as well as a science program?
I think the CubeSat opportunity is quite open. So there has been a call for ideas, a call for proposals, and we received 18 suggestions. And there needs to be some industry involvement, and at the end there needs to be some national funding for it. But I think there are no general restrictions on who can participate to it.
Any further question? No? Anything, Anita, from the social media?
Just before we finish up, if I might just ask Chris Russell another question, which is not about water. You won't be too surprised by this question, where I'm coming from on it, but I'm curious, because we're obviously in Europe, to hear your views on involving young researchers in space projects, because Dawn has been notable for the number, particularly of posters at conferences, LPSC and the like. We saw the same with Messenger. There are some members of the American community who've worked extremely hard, you being one of them, to include younger researchers in your project. So I wondered if you had any general advice to give to the broader community about how people devising instruments and missions can get that young generation fired up by actually getting their hands dirty on asteroids and planets.
Well, I personally, and I think many of the young people today find space very interesting. It's really an approachable but a frontier of our exploration, and we live in a very good and important time for the exploration of space. I personally have profited very much by chance of just I started in space exploration right out of college and continued through graduate school and my entire career, and I think that this opportunity really does exist for the best and brightest of our young people, and we should make those opportunities for them, get them involved, because the timescales involved in space exploration are very long. And so it's not something that you come in, work for a couple of years, and you make some major contribution. You have to work now for decades to get these missions developed, get to the target, and then analyze the data. So it really is valuable to be young when you're starting this business.
Any more questions? By the way, there are some EPO sessions here at the EPSC that are very interesting, where you will find activities that are done on outreach.
No, I really like this mission, this meeting, because of it's attracting the young people to space and making it approachable for them, and to see them there in their excitement is really something very good.
So, if there were, is there any question? No. Okay. So, thank you everybody for participating, and have a nice EPSC.